Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, The Key to Operating a Cost-Effective Industrial Compressed Air Station. My name is Amanda and I will be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, KAESER Compressors. KAESER Compressors is one of the world's largest compressed air systems providers and compressor manufacturers. From its state-of-the-art production facility in Germany, KAESER works in close partnership with its customers to develop progressive system concepts that continuously push the boundaries of performance and compressed air efficiency. Furthermore, over 100 years of knowledge and expertise has made available to each and every customer by the group's global team. Established in 1990, KAESER Compressors Australia services the Australian, New Caledonian and Pacific region from its purpose-built factory in Victoria. In addition, KAESER has sales and service centres and a dedicated network of authorised partners strategically located throughout the region that provide comprehensive sales and service support. The KAESER product range meets and exceeds Australian conditions and regulations, and the standard machines are suitable for continuous operation at ambient conditions of up to 45 degrees Celsius and higher. Today, we will hear from two speakers, followed by our live audience Q&A session, and I encourage you to send questions through to our speakers via the YouTube chat box during today's presentations. I'd now like to welcome our first speaker, Jeff Coyle. Jeff is the National Design and Engineering Manager at KAESER Compressors Australia, a subsidiary of one of the largest air compressed systems providers and compressor manufacturers. Jeff holds a degree in mechanical engineering and has over 14 years of experience in the compressed air and blower industry. He leads the National Design and Engineering Department at KAESER, supporting the broader community within Australia and New Zealand, as well as specialising in designing, engineering and manufacturing custom products for a large infrastructure projects, mining applications, etc. Please welcome Jeff Coyle.
Hi everyone, my name's Jeff Coyle and I'm the National Design and Engineering Manager at KAESER Compressors Australia. And in this session, I'm going to be going through the true cost of operating an industrial air compressor system. Let's launch into it. So in this session, I'm going to be covering four aspects. Number one, ensuring that you have the right technology for the application. So it's pretty important in selecting new capital equipment, as well as what are the true life cycle costs of a compressed air station, going through that in detail. And then number three, in an industrial setting, are budget compressors worth it in the long term? And wrapping up with correct maintenance and genuine spare parts. Let's get into it. So obviously for this presentation, I'm going to be talking mainly about industrial compressors. So in front of us there, we have a typical medium to large industrial air compressor station that you would see in heavy industry, manufacturing, mining, power generation, that sort of thing. So we have two large compressors there, possibly duty standby on the left. And in the middle, we have a couple of refrigerated air dryers and some small filters on the pipe there. And we have a silver tank, compressed air receiver tank. And at the end there, we have the discharge pipe and some oil water separators. So there's many items that come together to make an industrial compressed air system. I'm not going to go through the design of such a system today. We're just going to be, highlighting some of the true costs of operating such a system. So the first part, ensuring you have the right technology for the application. So in essence, which compressor do you use? And obviously we have many different technologies out there. We have, your small garage piston compressors. We have diesel-powered compressors, electric-powered compressors, oil-free compressors, lubricated screw compressors. So there's a large, array of compressors out there in the market, and it's very important that you get the right technology, because different technologies do, have different operational costs associated with them. So that's where, you might want to speak to experts in the field, like us at KAESER, or, speak to, say, if, for example, you were getting a packaging machine, that packaging machine that uses air would have, recommendations in there for different technologies and different air qualities. So you can use that to guide you to the right technology. And here are the technologies that are available for compressors in the world. We have dynamic compressors on the left there, and they're typically, larger style compressors, oil-free, like a turbo compressors where they use kinetic energy to create pressure. So very specific sector there for large mining and pharmaceutical companies and large manufacturing. On the right, we have the displacement compressors. So they're broken into two subcategories there. Obviously, on the right, we have the piston compressors, which we would know, from our garage compressors. And some oil-free piston compressors have specific industries as well. So, when we're at the dentist and we're hearing those drills grind in our mouth, they're often powered by a small oil-free piston compressor. And they all have different operating costs, but a very specific industry there. And in the middle, we have rotary compressors, and this would be the bulk of, the industrial market, and where we have one shaft compressors there, where we have multicellular, which is like a hydrovane compressor, sliding vane, liquid ring pumps, and spiral compressors. They're oil-free. They have very specific markets there as well. And then the two-shaft rotary compressors. In the middle there, we have the traditional rotary screw, and we have a lobe blower and a claw compressor. So, they come in different technologies as well, for different applications. And here's how some of those applications fall into performance. So along the bottom axis there, we have flow rate increasing, and then the vertical axis, we have pressure increasing. So you can see, at the top there, we have, piston compressors for high pressure, and that's really where that technology comes into play. For multi-stage pistons, for diving, PET bottling, so PET, where we're blowing out bottles into molds. They really can only do that with a piston compressor. And then in the middle there, around the 7 bar, that's our industrial pressure. And we have our screw compressors and those sorts of more commonly seen industrial compressors. That industrial compressor, I'd say, have a flow from anywhere from half a cubic meter right up to 100 cubic meters. That would be very typical of what we'd see in industry. And then down the bottom for pressure, we have like blowers, and they're typical in wastewater treatment plants, sewage treatment plants, for pneumatic conveying. They only really do 1 bar pressure, but they can do very large flows, and they do it very, very efficiently. So very low operating costs for a blower, and that's why they're popular for that low pressure sector. So very important to get the technology right when you're looking at these different types of compressors. And it's also worth looking at different technologies for drying the air. So a large part of an industrial compressor station is air treatment and dryers to remove that condensate, because obviously when we're compressing air many times, we're actually concentrating the amount of humidity in the air, making it a bit more of a larger problem than it is when it's at atmospheric pressure. So we need to remove that humidity, and we do that via dryers. And there's different types of dryers. We have diffusion membrane dryers, sorption desiccant dryers in the middle there, and then we have condensate refrigeration dryers, and they're pretty typical. So just as a bit of an example, a condensate dryer is much more efficient and has much less energy costs compared to the desiccant dryer down there, pictured the twin tower heatless desiccant dryer. Desiccant dryers need to purge, and they can lose 15% of the air fry that purge. So that adds to the operational costs drastically. So you really need to hone in on what air quality you need to be able to reduce your operating costs here. And that's key here for different types of for dryers and also filters. And thankfully, here we have the ISO 8573 have come to the party and given us some benchmarks for different air qualities. So we have the classes dictated there in the middle, where we have sort of 141 at the top. This is where, if you were to buy, say, a packaging machine, they may give you these classes of air quality. It's important to know that so that we can get the minimum amount of air treatment in there, because we don't want to have too much air treatment, because that would obviously increase your operational costs in changing filters, but also the differential across the filters. And when we have higher differential, we have higher running costs. And I'll highlight that a bit more in future slides. We'll do some examples of increasing pressure, what that might cost you. But you want to have the minimum amount of air treatment to do the job so that you can reduce your operating costs. So we've got charts like this from the ISO that can guide us on the best type of technology as far as air treatment goes. So moving on to part 2, the true life cycle cost of a compressor station. So before I get into that, we obviously need to understand how much air compressors use in industry. And when I first saw this slide, I was actually quite surprised because they do use a lot of energy, I guess you could see, in the industrial sector. So here we have figures for Europe, but I guess it's somewhat translatable to Australia. We have 18% of the total electricity used in industry in Europe is for air compressors. So that's quite a lot, we're more than fans, we're much more than refrigerant compressors. So it's really a sector in industry that we can really look at to be able to, I guess, improve the efficiency and improve the bottom line of businesses here by, doing some quite, easy things to be able to recoup some of that energy costs. And James, in the next presentation, is going to be highlighting some quite easy things that you can do in the compressor station and in your factories to be able to recoup some of that cost. So it's definitely worth looking at, and that's why we're here doing presentations like this, to really highlight the importance of having high efficiency and low operating costs compressor stations. So here's one of my favourite slides. It sort of paints a picture of the true operating costs of a compressor. You can see right there at the top in the red, we have energy costs. So this example, you can see the figures for the example there on the right. We have, say it's a medium to large compressor at 20 cubic meters a minute. It's only running 2,000 hours a year. So that's one shift. It's not a lot. Working pressure is 7.5 bar. And it's for 5 years, this chart. Our energy costs there 15 cents a kilowatt hour. And we've got some air treatment there with a refrigerator dryer and a filter to get to those class. It's 114. So you can see 63% of the operating costs of that station is for the compressor's energy. and that's only 5 years. So you can imagine 10 years' time, that's going to get exponentially larger. You can see the compressor investment cost there is 13%. And then you've got maintenance costs there for the treatment components, and those sorts of things. So you can see, it really highlights where you should be paying attention, in your compressor station too. And that, can play dividends, especially if you're looking at, purchasing new compressors. Where would you be better off focusing your attention on purchasing a compressor? Should you be looking at, how energy efficient that unit is? Absolutely, you should be. And this paints a very valid picture as to why, because that's where your dollars are going to be going in operating, is just paying your power bill for this compressor. So there's some really good food for thought there. And this is continuing on. This is a very, rudimentary or very basic, example here where we have the same compressor. It's 110 kilowatts. In this example, we're running 2 shifts. And this is purely to put a number on what it might cost to run this machine. And this is obviously going to be running it flat out for those 2 shifts. Down the bottom, we have a very basic power cost calculation there. And you can use this to calculate the power of anything. Like if you were to buy a new fridge at home, if you wanted to find out how much it might cost to run, you can use an example like this. So very, very simple. We've got 100 kilowatts multiplied by 15 cents a kilowatt hour, multiplied by how many hours to run it a year. So in this case, 4,000 hours. And to run that compressor fully loaded would be $66,000 a year. So you can see it, it adds up quickly. So, really important to look at energy efficiency. You're looking at, upgrading a compressor, or even just looking at trying to minimize its running through various means. So here's continuing on with that example. I hinted on, having the least amount of filters in the system. And the reason for that is that we want to reduce the pressure. So you want to run these compressors as low as possible pressure. So this example, I'm just highlighting, if we were to increase this compressor's pressure by 1 bar only, let's see how much that costs us in additional, money to power it. So we're going to increase it by 1 bar, and that's going to take 6% more energy. And that equates to 6.6 kilowatts in this example. So down the bottom, we've got 6.6 kilowatts multiplied by 15 cents a kilowatt hour, multiplied by 4,000 hours a year. And that's going to almost be $4,000 in additional power. So you can see, having the least amount of filters in there as possible, having the least amount of restriction in there, and also, having the least air leaks as possible, is going to greatly reduce the operating costs of such industrial systems like this. And here's an actual real life example that we've done. Obviously, I can't, have names or anything in here, but it's for a larger site in Victoria. And we've got a graph here where we have a histogram of flow, flow figures across the bottom there. And then on the right axis, or the left axis, I should say, we have specific energy of those 4 examples. So we've simulated different types of compressors or different technologies of compressors with software that we have available. That we've obviously logged this station and obtained that histogram. Now we're putting different scenarios of different technology compressors overlaid over that histogram. So you can see there is a big variance, and that's just within KAESER's product portfolio. We're not talking about budget compressors here or anything like that. We're talking about proper industrial compressors. See, there is a big variance in specific energy, specific power on the left there. So it's important to really do some logging like this and come up with histograms so that we can really hone in on what technology would suit that profile. Because there's not there's no silver bullet for compressor design. There's no 2 stations are the same. We really do need to look at it and do a custom solution for different flow profiles. This is the same example. We've got the different scenarios there. We've got the existing station on the left there, and we're looking at the kilowatt hours there. So you can see there are different, charts there that we have for different examples. We can see that we have, obviously with new modern equipment and master controlling there with our SAM. You can see we're really shaving off some kilowatts there. And here we have it in dollar form. So you can see with our best combo of compressors, and we're talking about combinations of different compressors to make up this flow. You can see we're nearly saving $50,000 a year there from the existing station, and that can be significant for businesses. $50,000 saving just for getting modern air compressors in there. That's every year you're going to be saving that. So, and also obviously going with modern equipment might be less to maintain, and all those sorts of things, which we'll cover a bit later on. So moving on to the next chapter, chapter 3, we've got in an industrial setting, are budget compressors worth it in the long term? And I guess, this really does depend on your application. I think in an industrial setting, certainly, probably budget compressors aren't that suitable, but it's going to depend on your application. So, for instance, your garage compressor at your house that you're using 2 times a year, budget compressors probably, that's fine. But if you're really relying on compressed air, and it's very important to your business, and you're using it maybe 24/7, probably want to invest in a proper industrial compressor. So I've just got some things to consider here, because every station is different, and every application is different. So there's no, silver bullet here for compressor design, but things you want to consider are, how often you use a compressor. If you're doing 3 shifts, 24/7, you probably want to have a good, proper industrial compressor. Also, how reliant are you on compressed air for your production? If it's very, very important, I remember we were looking at quite an important site, and if they didn't have compressed air, their production the whole site was going to be dead. And I think it was like $2 million a minute the company would lose if they didn't have the air compressor. So obviously, that's very important. So you want to have, backup, duty standby, but you also want to have good quality systems there that you can have service support for, and all those sorts of things, which I'll cover a bit later on. And also air quality. How important is air quality to you? If you need very, very dry air, because that's going to significantly impact your operational costs if you're going to go to desiccant dryers. So making sure that you don't need having the least amount of air treatment as possible. Obviously, efficiency comes into play with more cost-effective compressors. Obviously, there might be something missing in a cost-effective compressor. It might not be as efficient as some of the more premium products out there, where premium products might have IE4 super premium efficiency electric motors in them. The graph I've got there on the right is an air end curve. So an air end is the pump in a compressor. And the bottom axis, we have the speed increasing. And then the vertical axis, we have specific energy, specific power increasing as it goes up. So you can see a premium compressor will have the pump running at its optimum operating point, or its best efficiency point there on the bottom. So you can get best efficiency out of it. However, more cost-effective compressors might be having a small air end in there, small pump, and revving it a bit harder, so it might be running up that right-hand side of the curve a bit more, and therefore your specific energy drops off. So little things like that, it's important to look at. When you have direct drive, belt drive, they all affect operating costs. Also, service and maintenance. What's the availability of spare parts for a budget compressor? Do they have spares held in Australia? What's service and maintenance support look like? Do they have either distributors or branches all around Australia that can support the product? Do they have engineering support, the future works? Do they have 24/7 breakdown support? Obviously, with service and maintenance, you want more uptime, less downtime. So important to look at those sorts of things in, selecting not only a compressor, but the company you're buying from. It's very important. And also, budget compressors may not have, smart, intuitive, compressor control inside. So on the left there, we have, internal control, and that's a PC-based control system. On the right, we have master controllers that control big banks of compressors, control air treatment, and all those sorts of things. So are they integratable and are they future-proof? You might not be using such systems now, but 5 years' time, you may need to integrate that compressor into your site control system or link it to a machine. Are they future-proof? And often budget compressors, don't have this sort of capability inside them to be able to be, future-proof. So important to look at that. Industry 4.0 is, where all these systems are going for industry to be able to be linked to, back to companies like us for service support and all those sorts of things. So it's important to look at those sorts of things. So section 4, correct maintenance and use of genuine spare parts. So I already touched on that a bit, but obviously you want to maintain these units as per the OEM guidelines, because obviously, it's much like your air filter on your car. If that's very clogged, you're going to be using more petrol. Same deal for an air compressor. If it's not serviced, it doesn't have the right oil, if it's not getting to the right temperature, these all affect operational costs. So you want to make sure that it's serviced when it should be. And, if it's in dirty environments, it might need to be serviced more regularly. So you want to be looking at all those sorts of things for an industrial air compressor. And as I said before, filters do clog up over time. Even if you're in a clean environment, line filters like that one on the right do clog up, and they have service intervals. And they vary from different technologies, from 100 hours there, right out to 12,000 hours for some activated carbon beds. So important to know the servicing and do it when it's when it's due, to make sure that these capital items are kept up to scratch and online and running as they should be. Here's a bit of a chart of different filters. Filter elements do have differential from new. It can be to 0.2 bar. As I said before, it's important to have the least amount of filters as you need to reduce that operational cost. Because every 1 bar we go up, that's 6% in energy costs, remember. So, and as filters get clogged, that differential does go up, as we can see with the graph there. So you want to have good quality filters in there, and OEM filters as well. So it's not just filters here we're talking about when we're servicing. There's obviously valves and those control valves in air compressors that need to be serviced because they can leak. So leakage is a huge, energy consumption in a lot of industrial stations, and James will highlight that in the next presentation. But doing service kits on valves is very important. Making sure your controllers are set to the right pressure as low as possible. Just keeping on top of filters to keep the differential lower. And just even the oil, having the right oil temperature or right viscosity, all adds to the operational costs. And also, obviously, use genuine spare parts. Obviously, if you're buying the spare parts from the manufacturer of the item, they're fit for purpose. And obviously, we've had many cases of compressors fail from the use of incorrect or just what we call pirate parts, non-genuine parts that are for the machine, but they're just not designed to the same quality, or they're very poorly designed. We had remember an example of a separator cartridge, and that's the larger filter there pictured on the right in that picture, a separator cartridge for an oil lubricated compressor. It was for one of our machines, and it actually didn't even fit properly. That lip on the top was too large and it didn't seal properly. So it passed a lot of oil and it damaged the machine. So they just haven't been, some of these pirate parts aren't tested and aren't fit for purpose. So, buying genuine spare parts is very important. Genuine oil, so you know it's right and you know it's fit for purpose. So I guess some final food for thought as I wrap up here. This could be a topic all of its own for a talk like this, but what if you could reclaim some of this energy? I spoke before that 96%, well, 63%, I think, of power, or the costs of operating a compressor goes to power. You could potentially reclaim, 96%. It's actually, in real terms, 70 to 96% of electrical energy back via heat recovery. So a lot of industrial air compressors have heat recovery options. It's where we could heat, so do space heating with the exhaust air coming out to heat a factory or something like that. Or more commonly, we heat up water to up to 70 degrees. So you can recoup some of this potentially lost operating costs back and use it for heating water for an application. Obviously, you have to have a specific application for this, but this could be a topic all its own for a talk like this. But it's worth keeping that in mind, that you can recoup some of that large amount of costs. For that example before, it was $50,000 in energy costs you could get back. So it's a bit of food for thought as I wrap up there. So really thank you for your attention, and it's been a pleasure to present this to yourselves. And thanks for listening.
Thank you, Jeff, for your insights. I'd now like to welcome our second speaker for today, Dr. James Neal. After a 16-year stint at the University of Waikato, including the establishment and leadership of the Engineering Energy Research Centre, James is now busy working full-time in the private sector to implement change with a wide range of industry clients and partners. James and his team work with a strong emphasis on a total integrated systems engineering approach to plant and process improvement that incorporates principles of energy efficiency, equipment, and process reliability. James has over 25 years' experience working both in industry and working alongside industrial project partners to deliver successful outcomes that deliver on improved energy efficiency, safety, increased process yields, and enhanced plant and process reliability. James has volunteered extensively both internationally and locally to better the engineering profession, including over 16 years voluntary service on various committees and boards for SMRP, BANZ and ESNZ. James is the current chair of the Maintenance Engineering Society of New Zealand. Please welcome Dr. James Neal.
Okay, thank you very much for that introduction this morning. It's great to be here. And just to reiterate, so we're going to talk about leak management for your compressed air systems today. So just a very quick overview. We're going to start off with some real basic fundamentals of why should we even care about managing our leaks. We'll go through a few leak reduction basics. Then we'll get into a little bit more detail around more active and hopefully proactive leak management options, share a few examples of elimination of other air waste streams, a few case studies, and then we're going to finish off with some careful cautionary tales about metrics and KPIs. Okay, so first of all, why leak management? Well, in real simple terms, it's the quickest win you're going to have with most of your site systems and utilities. Very short paybacks, typically under 3 to 6 months. In a lot of cases, it can be down to a matter of weeks. If you've got a system that might be under a bit of strain, generally it's not too uncommon to find that you can also free up a compressor. And so instead of thinking about going to raise a capex to buy another compressor, you can generally free things up. And then, of course, as a result of that, you can generally lower your maintenance costs, especially when you're servicing your machines on an hour-by-hour basis. Now, I know depending on which part of the compressor business you're talking to, they might not like me saying that, but it's often a really good win to free up that capacity. Now, that being said, the big other win there that I've skipped over, which shouldn't be, is that it's a great chance to reduce your base load energy consumption on your site. So if you've got a power bill that you're starting to be concerned about, I know certainly on this side of the ditch that's becoming more and more of an issue. Depending on which part of Australia you're in, that might be a bit of a hot button topic for you as well. And so it's a great way to drop those kilowatts off your base load power consumption. Okay, so I've thrown in a couple of examples here, and it was interesting as I went back and reviewed the last time I gave this presentation and used some of these numbers. I had to upgrade the power price somewhat significantly. If we consider a relatively small user, and let's say you've got a 50 kilowatt system, if you've got a leak rate of 30%, which to be fair is actually quite conservative, that would be probably a pretty good outcome for most. And if you leave that compressor running all year round, and at 20 cents a kilowatt hour, you're talking about $26,000 a year that's just being wasted up into thin air. Now, if you go to a bigger site and you've got a 250 kilowatt compressor, you've probably got a 15% leak rate, would be really, really good. Multiply that out and you're getting closer to 32,000. Now, I do believe I've done that at a price of 15 cents rather than 10 cents. And I apologise, I think I haven't changed the 10 to a 15. But those astute people out there with a calculator, if you run the numbers, I think you'll find that that's actually based off a 15 cent per kilowatt hour, or for some of you, you might be more familiar with, say, $150 a megawatt hour. And once again, 15% leak rate is actually quite modest, and that wouldn't be you'd struggle to find too many sites with a leak rate lower than that. So you can see that these numbers can add up very, very quickly. Now, here's a little bit of a thought, and it's a bit of an oddball one to throw in here, but hopefully you'll understand why. And before we, you're probably thinking leaks. James is going to talk about how to find leaks and doing a leak survey and talking about how to fix the leaks and so on and so on. And yes, we're going to address that today, but here's a really basic number to try and wrap your head around. Now, obviously, 24/7 operation, and you can't shut anything down, then fixing the leaks is the only way. Now, if, on the other hand, you're a 2-shift per day, 5-day per week operation, so that works out at roughly, say, 80 hours a week. And if we throw on an extra shift for some maintenance to happen, say another 8 hours, we're at 88 hours. But of course, it's 168 hours to a week, which means you're only running your system, or need to run your system, 52% of the time. Now, if you switch your compressors off, then straight away, without spending a single dime, dollar, penny, cent, you can cut your leak rate virtually in half, 48%, just by switching the machine off when it's not needed or not required. Now, the question is are you even set up to be able to isolate your plant when it's not in use? Now, equally, this might apply to systems where it might be one part of the plant, one part of the factory, or you've got a special production that might only be running a couple of shifts, whereas the rest of the site might be 24/7. Can we isolate the system to that part of the plant? Now, some of you are thinking, oh, yes, but our fire systems, they need compressed air all the time, and we don't want to isolate that. And so, once again, if you're running a 250 or 500 kilowatts of compressed air, and you're keeping that on, and with all of the pipe work and leaks and everything else, just to maintain pressure to a couple of critical control valves on, say, your fire system, your water, etc., well, maybe it's a time to think about having a dedicated localized system that you can use to maintain that, which would probably only be a couple of kilowatts, and then you can isolate the rest of your system. So it's really, really important, just really back to the basics, is what can we do, and is there a simple way that we can actually make a big cut into our leak rate straight away with minimal effort chasing every last leak across your plant? Okay, so we've done that, and now what we're going to talk about today, which is really the guts of the problem, is what are our different options available to us to manage our leaks. Now, obviously, if you've got compressors that are coming offline, can we actually keep them offline by turning things off so that they don't have to load up and feed our leaks? Obviously, we talked already about isolating the plant. Are we just relying on our own ears? Are our maintenance guys just wandering through the factory during that maintenance period trying to listen, hear what they can hear, and then being able to fix that? Are we using the old soapy water test? Or, hopefully a lot of us out there nowadays are using the modern technology with ultrasonic leak detection. And the great thing about that is it's very directional, works even in a noisy plant. And we're able to do everything that we need to do while the plant's running. And the good thing, of course, is it finds those leaks that you won't hear audibly, but will actually be costing you money. There's plenty of leaks in what I call the sweet spot, in that 40 to 60 dB ultrasonically, and those leaks might be costing you anywhere from $300 to $600 a year, and you will struggle to hear them in the factory. And in fact, a 40 dB leak, if you go up to it and it's tagged, you will only just barely be able to feel that leak. Yet that will be a $300-400 a year leak, and ordinarily in a lot of cases very, very cheap and cost effective to fix. So really, really good technology. We're not going to talk too much about that technology today, but just a shout out that there are better tools available now for you to be able to keep on top of your leaks without needing your plant to be shut down. Okay, and so from a strategy point of view, are we looking to find and fix the leaks? Or are we looking to measure and then track, which is where your ultrasonic gear starts to come into the play? And of course, if we start to do that, can we then start to introduce some more proactive solutions where not only finding and measuring and then fixing, but can we then be a bit smarter with that information and make some proactive decisions on various things? And we're going to talk a little bit more about that today. Okay, so some leak survey fundamentals. What we need to think about to start with is what's the location of the leak? How are we going to track that? Are we going to break our site up into multiple plants? Are there some sensible sublocation categories that we might want to think about? Now, there's a couple of really good reasons why we want to do this. One, we want to be able to track and understand where our leaks are coming from, perhaps also highlight some focus areas that we might need to address. Or it might be that you've got multiple maintenance personnel or even operations personnel where we can highlight that there's maybe some training or some practices that we might need to sharpen up where we've got problems tied to a particular person or a particular procedure that may not be quite correct. Then, of course, we can then start to once again look into characterizing our leaks in terms of pressure, the different types of leaks. Then we can start to work on what sort of leak thresholds we're going to tolerate. Bearing in mind, of course, that best practice doesn't necessarily mean a leak rate of 0, but it's about understanding what actually is cost effective for you and your site, given not only the industry you're in, but also the age of your equipment and what you've got at your disposal in terms of resources. Now, when it comes to fixing the leak, you might want to also note down additional factors that might determine the cost benefit of whether you actually fix that leak or whether you leave it for a time. Now, obviously, access becomes important, both in terms of how easy it is to get to the leak. It might also be an environmental consideration. It might be whether you can turn the plant off to make the fix, or whether you can isolate the system locally and let the rest of the plant run, or whether it needs to be planned for an outage. Now, depending on the industry, that might be a bit of a challenge as to planning and coordinating when that gets done. But of course, having that information as well as where the leak is can be useful. And really smart operators will also take the time when they're doing the leak survey to think about the resources that may also be required. Okay, so key considerations once we've looked at our leaks is, well, one, how many have we actually got? Looking at our workload in terms of managing our workload of our staff. Is it something that we outsource? We're going to do it internally. Now, of course, if you've measured the leaks and you've characterized them, you'll be able to put a dollar cost against them. And then if you've noted down what you're dealing with, you'll also be able to look at an estimate of what your repair costs are going to be, which then enables you to do a potential payback or savings calculation. And then, of course, coming back once again with, do we need to isolate the plant to then be able to make the change, or can we actually make a big chunk of the savings by just isolating rather than having to make the repair? Okay, so you then might want to look to prioritize the work, obviously largest leaks first, and then I guess this is where the smarts can start to get a little bit more helpful in terms of identifying common areas, common faults. Might be a personnel related thing, could be a procedural related thing, could be an environment related thing, and then looking at, are we repairing or replacing the equipment? We had a site, just to digress briefly here, that had done a great deal of work in managing their leaks and getting on top of it, but by developing a lot of the background information, they were saving in the vicinity of $80,000 to $90,000 a year. That actually switched off a 250 kilowatt compressor through the leaks that they'd saved. Now, of course, the site manager was able to turn around and say, great, here's $80,000. We want you to make some improvements to the system. So they were prepared to reinvest the savings into the system. Now, of course, it wasn't a blank check. They needed to justify how they're going to spend the money. But of course, they were able to highlight a couple of key areas on the site that were their main problem children, or their bad actors, if you like. And what they were able to do was to come up with a proposal. Instead of using replaceable fittings and push fit fittings and flexible tubing and the like, they hardwired that part of the plant in stainless steel. It was a food plant. It was a key part of the factory with their cleaning in place, or the CIP kitchen. Obviously, a lot of acid, a lot of caustic soda and the like, so a lot of nasty chemicals. And so they're able to pinpoint they had a range of challenges with the environment, and so they were able to rebuild or replace that part of the plant so that they could prevent or eliminate those leaks from reoccurring. And of course, with good justification, site was happy to sign off the investment, and they were able to go from a find, fix, repeat to a find, fix, and eliminate strategy, which is really, really good for the long term. Okay, so fixing the leaks, I think this is a really good point to highlight today, is no leak survey has ever saved anyone any money. The only way to save money is actually to repair the leaks. And of course, we need to follow up to ensure all repairs have been completed correctly. And the old motto, if you're going to do it right the first time, and be a little bit creative and think outside the box. There might be some alternatives to how you go about this. And in fact, the one piece of advice I'd give to anyone out there today, if you're having a conversation either internally or with an external service provider about, hey, look, let's do a leak survey, let's save some money here. If you can't answer this one question, and that is, who's going to fix the leaks and when? If you can't answer that question, don't even start. Because you need to be able to have a plan in place, and without that plan, you are just spending more money. And really, really important, I can't overemphasize this point enough. You really need to be smart about this and make sure you've got a plan to execute the repairs from the get-go. Okay, now this is where we get into the hidden gold mine, which I've sort of alluded to with our food processing example that I just shared a minute ago, and that is the individual leaks collectively, they can tell a story. They can help you to identify some common themes or some common problems, highlight areas of concern or perhaps focus that you might need to have. And then, of course, we might then also be able to link that to some process inefficiencies. There might be a quality issue, a reliability issue. Is there some functional failure of the equipment because the air pressure is not able to be where it needs to be because we've got some leaks locally? We might be reducing the plant capacity. They might be slowing the plant down to compensate. All of these other things can tell a story to help you to understand where we need to prioritize our efforts, or perhaps like that example I just shared a minute ago, where you might need to redesign and replace some parts of your system so that it's more efficient and resilient and reliable. Now, furthermore for that, you might be able to identify some root causes of failures. or in this case, leaks. And you might be able to identify some common causes underlying that, be it environment, might be chemical, could be heat, could be UV with equipment outside. And then hopefully that can inform your purchasing decisions. Might be a problem with inadequate staff training. The person, and we see this unfortunately all too often, a flexible piece of tubing that's too short and pushed into a push-fit connector, and instead of the tubing being nice and straight, it's at an angle, and of course that connection is going to leak and leak readily, and you're going to have no end of problems. And so good staff training in terms of how to correctly install a fitting, how to correctly install tubing, and the other favourite of mine is compressed air tubing is often seen as a great thing to tie other things off to support weight that it shouldn't be used to support. So poor plant design, installation practices, and it might be you've got some dynamic system loading issues as well that you might need to think about. But as you go around and you're looking at the system, really, really important that you can find common issues that if you address it once, then you can actually put those things to bed and make your life easier in the long run. Often something that's glossed over by plant designers, specifiers, how often we spend only $1 on a cheap plastic air fitting when just a couple of dollars more can make the world of difference in terms of serviceability. And it's really quite telling when you think about the cost of the fitting might be a couple of bucks. The labour hours in terms of going to make the repair might be $50 to $100, and that leak might be a $500-600 a year leak. Where is the false economy in terms of buying a $2 fitting versus a $6 fitting? You don't need necessarily in a lot of applications to spend $30 on a fully bulletproof stainless steel fitting. In a lot of instances, a middle of the range $4, $5, $6 fitting will do almost as good, have more than acceptable service life, but obviously a lot cheaper than the full expensive sort of $30 premium fitting, but far, far better than the $1 fitting. So it's about understanding getting our purchasing decisions right for our applications. Okay, so what we're going to move on to today is we can't talk about leaks without also talking about the other waste streams, which I would also consider leaks. And so the two we're going to talk to about today are artificial demand and inappropriate use. So first of all, artificial demand we define as excess demand above what is actually required. So I guess let's translate that, break that down. Simply what we're saying is unregulated end-user compressed air, where we're using higher system pressure than what we need, which then ultimately leads to a higher demand. Remembering, of course, if you think back to your fundamentals of thermodynamics many, many years ago for some of us, that flow in terms of absolute terms is directly proportional to the absolute pressure. So as we increase the pressure in our line and our system, any leak is going to leak that much more, and so we're going to use more air from the compressor. Okay, so what does this look like in practice? Well, here's case one. Let's consider for a minute some pneumatic control valves. Typically, they might be 4.5 bar required, and so normal use, we're probably using 6.5, 7 bar. In most cases, this is unregulated. You're just going to use this straight off your ring main. So what's the cost? What's our acceptable safety margin? And what are the safeguards? And we'll just break this down for you. Okay, so for a pneumatic control valve, 4.5 bar with a 7 bar supply, if we regulated our 7 bar down to 5 bar, we're going to save 25% of our air use just in that one valve alone. If we regulate to 6, it's half that, 12.5%. So straight away, if we're using far higher pressure than we need to, we're actually using more air than we need to, and that's what we'd consider as artificial demand. Now, you might not, you want to drop the pressure that low, and so you might want to think about, well, what safeguards can we have in place? And this is where we start to think about extra system storage, especially localized storage, maybe better system controls. And Jeff has talked today a great deal about having a good, efficient compressed air system, and obviously good control is a key part of that, storage, and of course backup capacity. So if a compressor trips for any reason, we've got another one there to kick in and keep our plant running. Too often, an increased system pressure is a very, very poor, high-cost insurance policy that doesn't actually give you the insurance you think you have. So just some food for thought today. Now, another example today, if we think about pneumatic conveying or blowdown, you see a lot of air being used for this. Well, one, we should probably avoid it, but let's say that we can't. Okay, if we're doing that at 6.5, 7 bar, but we only need to do it at 3, what's that really costing us? So really quickly, if we're using 3 bar, but we're doing it at 7, if we do it at 3 bar instead, we can actually halve our air usage. Just right there by regulating that supply down, massive drop in air usage. Now, you might go to 3.5 bar, have a bit of headroom. We're still at 43, 44%. If we go to 4 bar, we're at 37% reduction. Okay, so really, really big gains to be made if you're smart about how you do these sorts of things. Okay, once again, you might want to think about some extra system controls. Now, one of the things to think about when you're using a high volume of air in these sorts of applications, you might want to think very carefully about not only system storage, but safety isolation, so that if we have a blowout on that system, we don't drag our whole system down, okay, and so that we can shut that part of the system off until a repair can be made without compromising our whole site-wide compressed air system. Now, of course, the thing down the bottom there, the point that I can't make enough is there an alternative? Can we actually use a dedicated blow line to do these sorts of applications? And then the savings are just absolutely enormous. Now, the next one is an artificial leak rate. So what we mean is that our leak rate that we've talked about previously is proportional to our system pressure. So our leaks are our leaks. We might not be able to fix them, but if we can drop our system pressure, straight away we can reduce our leak rate. So what does that look like? Well, let's say we need 6 bar from our compressed air system, but we're supplying it at 7.5. We've got a few anxiety issues, and we're thinking, well, let's just be on the safe side. We'll crank the compressor pressure set point up a little bit. So if we lower from 7.5 bar down to 6, we can actually make a straight across the board, across our entire system, a 17% reduction in our air use. Now, if we go to 6.5 bar, we'll drop to just under 12%, and we drop just half a bar, we can gain 6% in terms of less air usage across our entire system. So once again, just even getting our pressure system right can make a big difference. Now, these numbers don't include the power savings that come from actually the compressor running at a lower pressure, and that will then double up on top of these savings. Okay, so how do we make these savings? Well, we need to fix our leaks, but if we reduce our system pressures, that's going to fix or reduce all of our leaks by that small percentage. And a bit of extra storage is going to help you to do that. You might need to look at your pipe work and perhaps your backup capacity in the system. Okay, so inappropriate use very quickly is there's all sorts of shortcuts being used out there, cooling of bearings, agitating tanks, air lancers for cleaning, vacuum generators, which is a personal pet peeve of mine, pneumatic conveying we talked about, drying, cleaning, personal cooling, and so on. Okay, so why does this happen? Capital cost, time pressures, the infrastructure's already in place, we don't need an electrician, we can just tap into the airline that's already there, and of course, until we run out of air, there's no capacity constraints. Okay, so how do we address the wastage? Well, a bit of education and training might be required. Can we come up with some suitable alternatives? Can we eliminate access? And often it's back to improving standards and workplace practices, otherwise known as, at the risk of bringing out the C word, looking at our culture and understanding what we might need to do to sharpen things up with our people. Okay, well, here's example 1. Here's a blower versus compressed air. So the blower on the right, large facility, water treatment station to the left there. The blower broke down, 37 kilowatts, and we thought, oh, well, we couldn't get it repaired straight away. Switched over, had plenty of compressed air capacity on the site. Let's just use compressed air to backwash the sand filters. So yes, we could do it with compressed air quite comfortably, but thank you very much at a cost of about $175,000 per year. Now, at today's power prices, this example, which is a couple of years old, it's probably closer to $250,000. In comparison, if we actually spent a few dollars and repaired the blower and revert back to the blower, we go from 175 down to about 32.5. Massive savings, but just people underappreciating the different efficiencies of the two potential ways of backwashing our filters. Really, really bad example, but unfortunately all too common. Okay, second one. We have a factory here. This one's actually an ice cream factory, and they have a plastic seal around the lid of the ice cream. And of course, we didn't want plastic that didn't get sealed properly being blown off into the freezer. So what do is we put some air lines there to blow air across the conveyor belt and blow any waste plastic into the bag. Now, of course, compressed air, yep, does the job. That's easy. But of course, smart, more efficient solution is a vortex amplifier. Could still do it with compressed air, but with a fraction of the use of the air. 80-90% reduction. This was a $12,000 a year saving. Payback was under a month. Or alternately, could just potentially have used a fan. So really, really basic stuff that if we get it right, easily done. Another all-time favourite here, the old air gun here that was taped permanently open because someone wanted a bit of air conditioning. Or this one here on the right is a stainless steel manifold that's been welded in a food factory. And you'll notice that we've got a leak tag here, but of course there was a pinhole leak there which had already been identified, but instead of fixing, we thought we'd make fun of our mate the welder who didn't do a very good job of doing the weld. So I don't know what's worse, the fact that the thing was leaking or the fact that somebody else on the maintenance team found it leaking and thought it was funny rather than actually doing anything about fixing the problem. That leak there was probably about $1,500 a year, and a couple of $100 to fix. And of course, yes, have some fun. Give a guy a bit of ribbing over his shoddy welding. Maybe have him shout the first round on Friday after work, but let's also fix it and put it right. Okay, so to finish up today, we're going to talk just a little bit about some KPIs and some metrics. So really, really important, we want to track and report our outcomes, energy savings, reliability improvements, might be on-product time, mean time between failure. Process improvements might be our production rate and quality. We want to document our results, and our historical trends can be very valuable for helping us to see and demonstrate the value of us putting in place our leak management program. Now, when we repeat our leak survey of the plant, we should have a formal strategy. How often, when, where, the scope, how are we going to trace through our work orders. We don't want to be finding our old leak tags in the plant. And too often we'll do a leak survey only to find that there's tags from 2, 3, 4 leak surveys ago on the same leaks that haven't been fixed. We really want to work to identify those bad actors. Is it a location-based thing? Is it a hardware-based problem with the wrong valve, the wrong fitting? Is it a procurement issue, or is it a personnel challenge where we need to train and upskill? Now, obviously, we want to work towards a process of continuous improvement, and we can customize our leak survey strategy to be area specific. We might be able to extend our period between surveys for some parts of the plants, but we might need to be a little bit more regular in other parts of our factory. Now, we can then also look to refine our leak threshold in terms of at what point are we going to fix a leak. Obviously, keep up to date with our personnel training and engagement, and then consider the role of multidisciplinary teams. Now, I know this is a bit of a cliche thing these days, but it really does apply in this instance. Do we have good engagement with our plant operators? Is there a lot that they can actually do to stay on top of this? And if we can get them working in with maintenance, we can have quite a big game changer in terms of getting things done. Okay, so I really want to finish off today, and this point I can't understate, is the fundamentals of air leak accounting. And you're probably thinking, what am I going on about here? Well, I want you to think for a minute, who pays for the leak survey and repairs? Is it maintenance or is it operations? And generally, in a lot of places, it's the poor old maintenance manager. It's coming out of his budget. Now, of course, the dilemma here is who gets to bank the savings? Is it operations? Is it energy? Or is it maintenance? And generally, it's not the maintenance manager getting credit to his budget for the savings he's made. And so you can get some very perverse outcomes where the stakeholders haven't got the right incentives. So here's a really good example. The maintenance manager, his number one KPI is that the plant is reliable and is running. And in most instances, our air leaks aren't going to stop the plant from running. And so if he's got a limited budget, he's going to want to spend that budget on the things that hit his metrics, which is the plant reliability. Meanwhile, the site energy manager wants to get the energy consumption down, but of course, he doesn't control the maintenance. And so you've got two different key stakeholders with two different metrics at cross purposes. And so unless we have the right conversation at the right level and align everyone's incentives and directives, we are going to struggle on a site like that to actually get these things done. So really, really important. We've got to get our metrics right and make sure the right incentives are in place for the right people. So in summary today, we want to start with our leaks. We want to make sure any air use of any significance is regulated to the right pressure. We want to use localized receivers without the pressure control where necessary. And we want to reduce or eliminate all inappropriate use of compressed air. And the really, really important one that we just finished off with there, make sure our performance metrics and KPIs are aligned with the desired outcomes that we're after. Now, if you need any more help, training or information on getting started, you can reach out to me. There's my email address there, jamesn@energysm.com. And we look forward to taking your questions today. Thank you.
Thank you. Thank you to our presenters this afternoon, Jeff Coyle and Dr. James Neal, some terrific insights. And Jeff was absolutely right in his presentation. We covered a lot of content, a lot of scope, and I'm sure there's more webinars to come in this space. It's now your turn to get involved. Please, thank you for everybody that sent through questions, either live today in the YouTube chat box or earlier on registration. And please keep those questions coming through. We've got about 20 minutes to cover off some questions. If we don't get to your question, I apologise, but we'll get through as many as we can. I now want to start with you, Jeff, and we've had a question that's come in from Kizitso, who's based in New South Wales, asking you, Jeff, how can one effectively determine adequate air supply for a given manufacturing plant? Jeff.
Yeah, thanks for that question. And it's a really important question. And to determine accurately, the health of the station, the existing station, obviously we would need to do some logging. And we can do that in many different ways, by putting flow meters in or assessing the condition of the compressors directly to generate charts that you saw in my presentation. So, and to understand, a compressor station is very important to get those charts. Obviously, to use the old doctor's analogy, the doctor isn't going to prescribe medicine to you without, looking at you first. So, as compressor experts, we need to, really understand the customer's needs and the customer's station and how it performs over time, to be able to, really recommend the best station there. So, yeah, obviously, logging a station. There's many companies out there that can do it and logging it the right way. But yeah, certainly there's many means to do that, and it would be somewhat site specific to how we do that as well.
Thanks, Jeff. And we might just stay with you for the next question. And it's a question that's coming from Albert, and Albert's in WA. Good afternoon, Albert, asking Jeff, what's the optimization algorithm? Thank you.
Okay, that's a pretty unusual question, but I assume he's talking about some literature on our master controllers. So I'll speak on that. KAESER and many other manufacturers do have master station controllers that do have algorithm-based learned behavior in them to be able to switch and control banks of compressors and air treatment in a very smart and intelligent way, as you've seen in both James and my presentation. Having correct control and lowest possible pressure is very important. And to be able to achieve that, especially on larger stations where you have multiple compressors, even Vsd compressors in there, we need to have some sort of higher smart control. And the most modern technology out there now involves learned algorithms. So we have a lot of complex, computations happening in the background in these PCs, and they are a true, quite a fast PC that we would have in the compressor station to be able to do these iterations. And there's many iterations per minute happening in these stations to be able to make assumptions about future, pressure and flow to make sure that we have the right compressors running at the right time, that they aren't fighting each other, and we're keeping the pressure as low as possible. So those sorts of, optimization algorithms are available in nice compressed air station controllers. And our such controller is called SAM, Sigma Air Manager. So there's literature on our website about that if anyone wants to learn more. But very important in a large, modern compressor station to have high control like that.
Thank you for that, Jeff. Moving across to you, James, we've had a question coming from Stratus, who's in New South Wales, asking you, James, are there any benchmarks for calculating leakage costs in dollars and carbon? Thank you.
Okay. Well, it's a really good question. And the short answer is if you're using the right ultrasonic detection gear and the right method, if you're trained, and I guess a small disclaimer here, I am a certified trainer in this space, and there are methods that have been well proven in this space. If you use a correct technique, you can relate the ultrasonic dB and based on the pressure to an estimated leak rate, which then based on your power cost, you can then correlate that to an actual dollar figure. And of course, one of the companies that I work closely with, UE Systems, actually patented this process a number of years ago. I'm surprised they actually patented it, but it was more about protecting their ability to do it. Their software they have actually then has the ability to also incorporate, based on your grid emissions factor, what that then correlates to in terms of your carbon emissions. So you can actually now get tools that are readily available for free, where you can do your leak survey, and then you can then get a report spat out with the leaks and a dollar figure against each leak, including both direct energy cost and then all your carbon costs and everything else as well. So yeah, there is a very good way to do that, very quick, very easy. And so if you're more than just wanting to just find and tag and fix and actually track and monitor, that is very much available technology.
Thanks very much, James, for that. Just staying with that emission theme, we've had a question again from New South Wales, from Philip, asking, Jeff, with 4% overall energy efficiency, is compressed air going to be phased out as we move to zero emissions by 2050? Thank you.
Yeah, thank you. It's an interesting question. It covers a few different topics there, but I'll talk to obviously, the 4% efficient. It's known that compressors do generate a lot of heat, hence why I mentioned heat recovery is an option there to recoup some of that cost. But as far as if we talk purely on industrial setting, compressor will always have a place in industrial setting. Obviously, it's inherently safe, and it's widely used in certain manufacturing. If you look at every single factory in industrial state, more than likely it'll have a compressor there. So the uses are very wide. And if we just look at, for instance, hand tools in an industrial setting, yes, there's been a rise in the electric battery operated hand tools that tradespeople use. But certainly for an industrial setting, if we're looking at big manufacturing plants, you still need to have air-powered tools there to some degree because they do have a much higher duty, and they are a bit safer than electric, hand tools. Certainly in a production plant where they're running multiple shifts, electric hand tools might not be that's safe. So yeah, it still does in industry have a certain large place there, and that's why we're moving towards better technology in compressors, having them be higher efficient because it certainly is there to stay. So and the applications are really infinite for compressed air in industrial setting, it's really exciting. But certainly looking to smarter systems to make sure that we use compressed air as efficiently as possible is the key there.
Thank you for that, Jeff. Over to you, James, and please, our speakers, please feel free to continue the conversation after the question's been directed just to you. But James, a question from Ki Ming asking about large ring mains. When designing a large ring main, when is it appropriate to include split receivers, compressors on opposite sides of the ring main? Thanks, James.
Okay, yeah, this is sort of an interesting question, and I might sort of try and answer a couple of questions in one go here. And look, when you've got a big facility, generally, if you've put a good ring main in and you put storage in the right place, generally you're better off having everything in the one location if you can, and purely and simply from a point of view of maintaining and actually then controlling the systems, it's going to work a little bit better. Otherwise, you can end up with compressed air fighting, and I don't know how well my hands are going to show. You can have air going this way, and then obviously turning around and then turning around and going that way. And so you end up with what some people might refer as negative flow, which is not necessarily a bad thing, but just good system design. You don't want two compressors fighting one another. So generally, you want to keep your systems together. Now, the one exception for this would probably be what I kind of alluded to in my presentation, where you've got a part of the plant that you actually want to be able to isolate and be able to keep one part running, but the other part can be isolated. You might then actually want to have a dedicated compressor over there so that then you can shut off the rest of your system. But yeah, generally on a big site, you've got a big ring main, and it's because your whole site's running around the clock. So if that's the case, I would try and keep your compressors together rather than scattered all over the place. If they are already scattered, and it's obviously a lot of money to move them all around, then you want to think very carefully about getting the right sized receivers in the right locations so that you can then look to base load some of the remote compressors and then still manage your primary control from the single air station, would be probably my recommendation there. Thanks.
Thank you for that. Jeff, we've had a question coming from Algis who's asking you, what are the advantages of oil-free screw technology Vsd compressors over standard technology? Thank you, Algis.
Yeah, thank you. It's obviously there's two parts to that question. He's mentioning oil-free compressors, which have a very specific industrial application, or many of them actually, and they're where we don't want any chance of any oil getting into the airstream. And those industries would be your food industries where the air is getting in contact with food, pharmaceutical industries, as well as electronic manufacturing. So that's where we would see those types of industrial compressors. There's obviously medical applications and some laboratories as well, things like your dentists. So they have a very specific niche sectors there that they would be used in. So they're the only industries that I would really use an oil-free compressor because they do have higher running costs and higher maintenance as well. So that's for them. And in regards to VSD compressors, all compressor manufacturers do offer those, and that's where the compressor may change its speed depending on the flow required. So they can be a fantastically efficient compressor, but it really does get back to the flow profile of the site, and whether that compressor's control range can, I guess, mate and marry up to the customer's flow profile to make sure that we have, it working within its sweet spot, because they do have sweet spots on their air end curve, and they need to run in that to be efficient. So, VSD compressor isn't a one size fits all, for that reason, that we need to ensure that it runs in its sweet spot, and that can be quite tight depending on the technology. So that's where understanding your flow profile is very important before we start talking about whether we need a VSD or multiple compressors or VSD and base load machines. There's many options there, but hopefully that's addressed your question. Thanks.
Thanks, Jeff. And just staying with you, but a question that came in from Alfie, but it is picking up on the training themes in the presentation. So I might actually direct it to you, Jeff, even though it came in for James, asking, industrial compressors in the production building here in Victoria, is there anyone from KAESER who can help us with the selection of the relevant compressed air systems requirements? And just to broaden that, what is the process when people are looking for some help?
Yeah, sure. Obviously, that's what we're here as a company to be able to assist clients with those sorts of needs. So obviously the first port of call would be to just reach out to experts like either companies like us or James to be able to understand your needs. That would be really the first point of call, is to do some sort of site assessment with logging to see where you're at. And then from that, we can have a look at what compressors you already have and how we can improve on that. As we saw James speak about, the first point of call would always be to sort of look at leaks and addressing those things, because that's your best bang for buck, as James said. And then if you need new compressors or replacement, obviously we can look at what current technologies might best suit. But certainly, the first step is to don't be afraid and reach out for assistance from experts like people from KAESER or independent people like James. Thanks.
Thanks, Jeff. James, we've had a great question that's come in from Rameshwari, asking you, what's the advantage and risk of using uncoated internal piping and galvanised piping for air distribution networks? Thanks, James.
Yeah, look, this is a really interesting question, and you could very quickly open Pandora's box here if you wanted to, but I'd probably throw it back a little bit. Jeff had some great slides in his presentation where he talked about the ISO standards for minimum requirements for your air quality, and generally that's a really good starting point to understand what you want to do. And the two examples I'll use very quickly here is, one is if you've got a nice pharmaceutical or high quality food grade facility, you're using oil-free air compressors and everything else, then you're probably going to be wanting to specify a good quality distribution pipework rather than just old mild steel or even galv steel is probably not that well suited. And this is where, of course, your treatment becomes important. You don't want to send anything down that line. I won't name the site, but a nutritional product making baby formula, a nutritional plant, had nice new compressors, beautiful stainless pipework everywhere, but someone missized the compressors, so they built the plant, they needed extra air, and they plugged in a portable diesel oil-injected screw compressor. And of course, the problem with that, didn't have a dryer, and the water separator and oil separator wasn't working too well. They pumped a whole lot of low-quality air with oil and water and all sorts down this nice, pristine, high-quality stainless steel line. So, you've actually got to look at this from a big picture point of view and understand, well, what's the standard? What do I need to meet? And then work back from that, both at the compressor station and then obviously that flows through to your pipework. So generally, if it's just a process air line, you still probably want to think about not having too much water in it, because your lines aren't going to last too long unless you're using a plastic line or something like that. Then you've got other problems in terms of how you might support it. So look, there's a whole raft of risks and rewards here in terms of saving cost, but I'd like to probably point back to the slide that Jeff shared in his presentation, and that's where at the end of the day, the capital cost of any of these things is always a fraction of the overall spend. And if you're thinking about this for a minute, let's say you've got a big overhead pipeline, and by the time you look at the finished installed cost of that distribution system, the actual capital cost component of the pipe material itself, once you've allowed for all of the installation and everything else, is only a fraction. You'd be lucky if it was 10 or 15%. And so even if you spent a little bit more money on a better quality pipe, I can guarantee you time and time again, the life cycle cost benefit of doing so will be immense. So yeah, I always tend to favour using better quality pipe because it's going to last. And obviously it depends on what's going down the line. Would be more than happy for him to send me an email with a more specific example of what he's looking at. But yeah, look, you do want to think very carefully. It starts with, well, what quality air do you need? And then you can start looking then at the life cycle of that asset. How long does it need to last? And with all these things, as I just said before, the marginal cost of using a more expensive, better quality, long-lasting pipe is generally going to always make sense when you look at it through a life cycle lens and start to look at it from a more balanced sustainability point of view, as opposed to just an immediate, cheapest upfront capital cost.
Thanks for that. And we are, as always, rapidly running out of time. But I just wanted to combine a couple of questions around leaks, and maybe James, stay with you. Jeff, you might want to jump in, asking, are there any online leak detection methods that can detect in real time? We've had another question is, what are the usual number of leaks, if that can be answered?
Yeah, okay.
James.
So real quick, your online detection methods can be quite varied depending on how you run your system. In real simple terms, if you know what your normal plant usage is, just a flow meter, and your operators are normally pretty good, you're going to know what it's meant to look like. And just with a simple flow meter, you can tell when your usage has gone up. That then tells you straight away that that you've got a problem. The problem with that, of course, though, it doesn't tell you where in the system your problem is. Okay, you can actually get permanent mounted ultrasonic sensors that you can mount in critical parts of the plant where you can pick up on leaks or other bits and pieces. Yeah, so look, you can do it, but typically you still need to find the exact location of the leak, and that's where your ultrasonic leak detection gear comes into its own, because you can find it very quickly. You can do it while the plant's running, and you can progress fairly quickly there. Now, there was another question there from Jamison, Amanda, that I might just hit at the same time, and that's where, yes, these same detection methods can be applied to vacuum pump systems. It's the same technology, it's just a slightly different technique, because of course the detector is detecting turbulence, and with a vacuum leak, the turbulence is internal, whereas on a compressed air leak, the turbulence is external. But yes, the technology can be used for both. And to finish off, the question with regards to number of leaks, rather than saying number of leaks, because you can find as many leaks as you want, and it comes back to what sort of sensible threshold. And I used a threshold in my talk. I mentioned 40 dB, and that's right on the cusp of what you could feel. And so you can imagine with a really good detector, I could find hundreds and hundreds of leaks on a facility. But of course, a lot of them, you're going to get people frustrated. Your maintenance guy goes out to fix the leak, the tag's there, and he can't feel anything leaking. Very quick to upset the whole culture of your maintenance program. They can get very disgruntled. So best to work on the bigger leaks. And as a sensible number to take away from today, once upon a time, probably 10% was considered a best practice leak rate. Nowadays, it's probably closer to 5%. And I'll just reiterate that the best practice benchmark for leaks isn't 0, And generally, if you've hit zero, it means you've probably overspent on the capital or the maintenance of your system. Now, there's always exceptions to these rules depending on the industry you're in and so forth. But for compressed air, you should be targeting an overall leak rate of sort of 5% or less. And generally, most facilities, if you go and do a leak survey, you'll find probably anywhere from 50 to 100 leaks fairly easily. And of those, probably 20 of them will be really big. The 80-20 rule sort of applies. But yeah, look, every site's going to be different. But you'll find that typically on most sites, half their leaks are fittings. The other common leaks are your regulators. They're probably your two main ones. Then, of course, depending on what sort of valves you're using and so forth. But yeah, a total number of leaks is a bit of perhaps probably the wrong question. But yeah, certainly the leak rate as a percentage, you want that at 5% or better.
Thank you, James, and thank you for answering those multiple questions together. Appreciate that. Unfortunately, it is all we have time for today. We could talk about this a lot more, and I'm sure we will at a future session. So please join me again in thanking Dr. James Neal and Jeff Coyle for their time and insights today. As always, we'd like to thank our Engineers Australia industry partner, KAESER Compressors, and for all their support. And without that, today's webinar wouldn't have been possible. Always, we'd like to get your feedback and ideas for future sessions. So if you could please quickly complete the feedback form in the chat box below. Thank you again for taking your time to join us, and we look forward to seeing you at a future Thought Leaders session. Thank you very much and good afternoon.